Uh, in this section, we're going to look at dynamics. Dynamics is the study of accelerated systems. This is the study of accelerated systems. So these systems are governed by Newton's second law that net force is proportional to acceleration. So Newton's second law implies that the net force acting on an object equals mass times acceleration. And if there are a number of forces acting on the object, then we can write this F naught as the sum of the forces. So we have F1 plus F2 and so on equals mass times acceleration. Okay, so these are the vector forms of Newton's second law. We can also write this in terms of position vector or velocity. If you remember, acceleration equals the derivative of velocity with respect to time. Okay, so we could write net force equals mass times derivative of velocity with respect to time, but also v equals derivative of position vector with respect to time. Okay, so we can say that acceleration, which is the derivative of velocity with respect to time, is the derivative of position vector with respect to time. Okay, so that tells us acceleration is the second derivative of position vector with respect to time. Okay, so another way of writing this equation is the net force acting on object equals mass times the second derivative of the position vector with respect to time. Okay. Now let's write these equations in component form. In component form, if two vectors are equal, then obviously their components are equal. Okay, so we can write this as the sum of the x components equals mass times the x component of the acceleration, and the sum of the y components of the forces equals mass times the y component of the acceleration. And then for the expression in terms of position vector, we have this vector equation d squared r by dt squared, and then we can say f net x equals the second derivative of x with respect to time squared, and the net y equals second derivative of y with respect to t squared. Okay, so these are the component forms of the two equations. All right, so let's look at some examples. Let's say the position vector of, let's say, maybe 2 kilogram object, let's say, varies with time, according to the equation. Let's say we have this dependence of position vector on time, maybe 2t squared plus 4t in the I direction, maybe let's say 5t in the j direction. Okay, the question is calculate the force acting on the object, let's say maybe after 2 seconds. Okay, so we're looking, the question is to find the force at t equals 2. Okay, but first we have to find an expression for the force as a function of time, and that is F equals mass times the second derivative of position vector with respect to time. We can say it's the derivative of the derivative with respect to time. Okay, so the derivative of position vector with respect to time from this equation for the position vector will be 4t plus 4 in the I direction, okay, and then 5 in the j direction, 5 in the j direction. And then the second derivative, that is d squared r dt squared, would be the derivative of this one, which is simply 4 in the I direction plus 0 in the j direction. Okay, so the acceleration is 4 meters per second squared in the I direction. All right, therefore, and of course we're told mass is 2 kilograms. All right, so this force over here equals the mass times the acceleration, which is 4I in the j direction. So the force acting at this object after 2 seconds, simply 8 newtons. Now let's take a purely mathematical problems. The following forces, let's say F1 equals maybe 2I plus 4j, F2 equals maybe negative 3I plus 6j, and let's say an unknown force F are acting, let's say on a 5 kilogram object. Okay, if it is moving with an acceleration, let's say of let's say I plus 2j meters per second squared. The question is calculate the unknown force. Calculate the unknown force. Calculate the unknown force. Okay, so we're going to use Newton's second law. Newton's second law says F net equals mass times acceleration. Now we have 3 forces. This is F1 plus F2 plus the unknown force F equals mass times acceleration. Okay, so that means the unknown force F is mass times acceleration minus the force F1 minus the force F2. Okay, so just plug it in. The mass is 5 kilograms. Okay, m equals 5 kilograms, 5, and the acceleration, so is I plus 3j. Okay, minus F1. F1 is 2I plus 4j. 2I plus 4j. Okay, minus F2. F2 is negative 3 in the I negative 3 in the I plus 6 in the J. Plus 6 in the J. Alright, so we just collect the I's together and the J's together. So we have 5 I's minus 2 and then plus 3. Okay, so we get 5 times I, 5 minus 2 is 3 and plus 3 6. So this is 6 in the I. How about the J? We get 10J over here minus 4J is 6J, and 6J minus 6J is 0. Okay, 10 minus 4 minus 6. That's it. So the unknown force is simply 6 in the I newtons. Alright. Okay, let's consider another example. Suppose we have the following. You get this object over here. Let's say it's a 10 kilogram object. Okay. Suppose, let's say we have these forces. This force is pushing this way, this is 10 newtons, and then maybe we have another force pulling back, 4 newtons. So the question is, A, assuming no friction, calculate its acceleration. If you know the acceleration is to the right, so A is going this way. Okay, the acceleration is to the right. Alright, so what are the forces? We have these two forces. Maybe let's give them names. Let's call this F1. Let's call this F2. Okay, we have other forces. You get weight pulling down. You get normal self pushing up. Okay, these are the forces. So, technically speaking, the Newton's second law for this motion would be this one. You add up all the forces, you got F1 plus F2, and then you got weight, you get normal force equals mass times acceleration. Technically, this will be the application of Newton's second law to this equation. Alright, but the object is going to the right, so we're getting only the x part of the equation. Okay, these two forces do not have x components. So the x part, we have F1x plus F2x plus Wx plus Nx equals mass times Ax, right? So these two forces do not have x components. So we can equate them to 0 because they're vertical forces. So this basically becomes F1x plus F2x equals mass times Ax. Okay, so what do you know about acceleration? We know it's going to the right, so theta A is 0, but we don't know its magnitude. So Ax is the magnitude of the acceleration times the cosine of 0, which is the acceleration. How about F1? What do we know? F1 is to the right. Once again, its angle is 0. And we also know its magnitude. Its magnitude is 10 newtons, right? So F1x is 10 times cosine of 0, which is 10. Okay. About F2, what do we know? Its angle is west. You see, it's going this way, so its angle is 180 degrees. So theta 2 is 180 degrees, and its magnitude is 4 newtons. Okay, so the x part of this force is 4 times cosine of 180. Cosine of 181 is going to be negative 4 newtons. So that's it. So going back to this equation over here, this equation f1x plus f2x equals max. You see, f1x is 10, f2x is 4, the mass is 10, and the acceleration is this magnitude A. Okay, So you've got 6 equals 10a. It follows that its acceleration is 0.6 meters per second square. All right. So B, we're going to say assuming the coefficient of friction, assuming the coefficient of friction between the surfaces, let's say is 0.2. Okay, so in this case we have coefficient of friction mu 0.2, which means we have an additional force of friction. Okay, so in this case we have another force of friction going this way. We have another force F. So the x part of the equation will have an additional force. So we have F1x plus F2x plus the x of the friction equals mass times AX would be our equation. Okay. So for friction, what do we know? Friction is magnitude mu times normal force, and its direction is 180 degrees. Okay, so we have already worked this out. F1x is 10, F2x is 4, and this will be plus mu times n cosine of 180 degrees equals 10, and AX equals the magnitude. We just saw that. Okay. All right. So we know this is 0.2. Okay, so far we have the following. 6, this is negative 1, minus 0.2n equals 10a. Okay, so we have to calculate the normal force. The normal force is a vertical force. So we need the y part of the equation now. You see these three forces do not contribute to the y component because they have y components that is 0 because they're horizontal. So we have only these two forces with y components. So the y part of the equation is ny plus wy equals, and the acceleration also does not have a y part. You see, its angle is 0, sine of 0 is 0, so this is 0. So this is the equation for the vertical part. So the normal force is looking for, its angle is 90 degree, the weight is mass times gravity, or 10 times gravity, approximately 10, that's 100, and its angle is negative 90. Okay, so we have the normal force times the sine of 90 plus the weight 100 times sine of negative 90 equals 0. Okay, so this is 1, n is negative 1 minus 100 equals 0. So the normal force is 100. Basically, the normal force balances the weight, so it's equal to weight in this case. Okay, so we go back to this equation. Let's see, I think this object won't be moving. Because the force of friction in this case would be 100 times 0.2 would be 20 newtons, and so this forces cannot move it. Well, let's continue. So in this case, what's going to happen is 6 minus 0.2 times 100 equals 10a, okay? But you see the force of friction is 20, so this force cannot move it. So the conclusion is it cannot move, okay? Because the force of friction is bigger than the force pulling to the right. We have force of friction with its maximum value is 20 newtons, but the force pulling to the right is just 6, so the object will not move, okay, because the force of friction is bigger than the force pulling, okay. So it's not going to move because the force of friction is 20 and this one is 6. It's not going to move. All right. Now let's look at another example. Let's have the same force over here. The same mass. Let's say it's 10 kilograms. Okay. Let's say this force pulling this way. Let's say it is 100 newtons, and let's say this angle over here is 37 degrees. Okay. So first we're going to assume no friction. A. Calculate acceleration assuming no friction. Okay, so and of course moving this way, so this is the direction of acceleration. All right, so we have the following forces. We have this force over here, but also we have the weight pulling down and normal force pushing up. Okay, so technically let's call this maybe F. Technically the equation would be F plus N plus weight equals mass times acceleration. But it's moving to the right. It's moving to the right, so we just need the x part of the equation in this case. Okay, so we'll say f1x plus nx plus wx equals mass times ax. You see these two forces, they do not have x components. All right, so we're going to say 0, 0. So basically we just have f1x equals mass times ax. All right, so what do you know about the force? The force F1, this force over here, its magnitude is 100 and its direction is 7 degrees. Okay, and what do you know about the acceleration? We don't know its magnitude, but its direction is 0. Okay, so this is 100 cosine of 37 equals the magnitude acceleration times cosine of 0. Okay, so this one is 0.8, so this is 80. 80 equals a, oh, forgot the mass. There is mass over here. Mass over here. So that is 10 times a. Okay, so the acceleration is 8 meters per second square. Okay, now we're going to say calculate acceleration assuming there is friction. B, calculate acceleration assuming the coefficient of friction let's say is 0.1. Okay, all right, now we have an additional force, there's friction, so we have this force over here, friction. Okay, so the equation technically would be you have friction, you have normal force, you have the weight, and then you have the external force equals mass times acceleration. Okay, so first let's do the x part. The x part is fx plus nx plus wx plus fx equals mass times the x part of the acceleration. Now the normal force and the weight do not have x components. Okay, so basically we have fx plus the external for x equals mass. This is our equation. Okay, So we just saw that fx is 100 times cosine 37, okay? And the direction of friction is 180 degrees, okay? So friction will be its magnitude times cosine of 180, and this one is 100 times cosine of 37 equals mass, which is 10, and ax equals to the magnitude acceleration over here, okay? So this is the equation, negative f plus 100 times 0.8 plus 80 equals 10 times acceleration. But the problem is we have two unknowns, right? But we know that the friction is mu times the normal force. So in this case, 0.1 times the normal force. So this equation becomes negative 0.1 times the normal force plus 80 equals 10a. Okay, but how do you calculate the normal force? The normal force is a vertical force. So we can calculate it from the y part of the equation. Okay, so this is the y part. The y part will be fy plus ny plus wy plus fy equals may. Okay, so remember this is the direction for this one is 180 degree. Okay, so its vertical component is going to be 0. It's horizontal. So this does not have a horizontal component. But these three forces have vertical components. Okay, so vertical, this is inclined. So this one doesn't have vertical component. Okay, so the equation is we have ny plus wy plus fy equals mass times ay. And remember, ay is horizontal force. The direction for normal force is 90, so we can say n times sine of 90. The weight is negative 90, and it is mg sine of negative 90. The force F is 37 degrees, so that is its magnitude is 100, and then times the sine of 37 degrees, and AY is 0 because this angle is 0. This will be A times sine of 0. Okay, so the direction is 0. So this will go away, this will be 0. This is 0. Alright, so sine of 90 is 1, so you've got n. And this one is the weight, mass times gravity. That's approximately 100 over here. So it's going to be minus 100 for the weight. The weight is minus 100. And then 100, this is 0.6 plus 60. Plus 60 equals 0. The acceleration is horizontal. It doesn't have a vertical component. Okay. All right. So we have this equation that is n minus 40, so the normal force is 40 newtons. All right, and then we come back to our equation over here. That equation was negative 0.1 n plus 80 equals 10 times acceleration. All right, so negative 0.1 times 40 plus 80 equals 10a, and then this is just negative 4. Negative 4 plus 80 equals 10a, so that is 76 equals 10a, or the acceleration is 7.6 meters per second squared. All right. Now we're going to consider an inclined plane problem. Inclined planes are very popular in physics. All right, let's look at an inclined plane. Maybe let's try it this way. Topic, inclined planes. Okay, suppose we have this inclined plane over here. Okay, suppose we have this object over here. Okay, so first we're gonna assume no acceleration. I mean no friction. A, assume no friction. Okay, so we don't have friction. So what's the force pulling it? It's obviously gravity. Okay, gravity is pulling down. Okay, this is a component of gravity in this direction that's moving it. But before we proceed, let me say something about coordinate systems. There's nothing special about the vertical horizontal coordinate system. Okay, you can rotate it, but when you rotate it, you have to make sure that the y is in a counterclockwise direction from the x. Okay, so you can do it like this with xy, but you cannot do it like this xy because y is not, in this case y is in a clockwise direction. Okay, as far as you make sure y is in a counterclockwise direction from x, it doesn't matter which way you put your coordinate system. Okay, so usually it's easier to put your x-axis in the direction of acceleration. So in this case it would be easier to use a coordinate system like this, the y and then the x going this way. This would be the easier coordinate system to use in this case. Okay, so suppose this angle is theta over here. All right, so the force is pulling it is the weight, and that is, let's say the mass of this one is m. This is m times g. All right, so this angle is theta. So this is our x-axis now, right, and this is our y-axis. All right, and angles are measured with respect to the positive x-axis over here. This is our x in this problem because we chose to use this coordinate system over here where y is in this direction, x in this direction. You see, y is in a counterclockwise from x, so this is a valid coordinate system. Okay, so if this angle is theta, this angle over here is going to be 90 minus theta. Okay, but that is angle measured in a clockwise direction. Okay, so the direction for weight is actually negative of 90 minus theta. Okay, so the weight, its magnitude is mg. Let's look at the weight. Okay, its magnitude is mg, but its direction is, that angle is 90 minus theta, but it's measured in a counterclockwise direction, so it's negative 90 minus theta. Okay, so you can say that the weight is mg cosine of negative 90 minus theta, or theta in the I direction, plus mg sine of negative 90 minus theta in the j direction. Okay, so you can expand this, but it's basically we're looking, these are the x and the y components of the weight. This is the x component, and this part over here is the y component of the weight. So this is under 90 degree over here. Okay, so this is the x component, this is the y component. So if this is 90 minus theta, this angle is theta. Okay, so this part over here, right angle over here, and this is the right angle over here. This angle is theta over here. So this is opposite side. It's going to be mg sine theta, and this is going to be negative mg cosine of theta. But you can just expand this one. We'll find this one. This is mg sine theta in the I direction minus mg cosine of theta in the j direction. Okay, this angle is theta. This is a right angle triangle, so this is the opposite side. It's given by, so this is mg, this is mg sine theta, and this part over here is mg cosine of theta, but the negative y direction is going to be negative. All right. Okay, how about the acceleration? The acceleration has a direction of 0 because the direction of the x-axis. Okay, so theta a is 0, and its magnitude, of course, we don't know, is a. So acceleration would be a times cosine of 0 in the I direction plus a sine of 0 in the j direction. So according to this coordinate system, the acceleration doesn't have a vertical component, okay? Because we we align the x-axis in the direction of the acceleration. So it's just a in that direction. That is, ax is a and ay is 0. Okay? And from this equation we have wx equals mg sine theta and wy equals negative mg cosine of theta. Okay? So now, what are the forces acting on this object? We have another force. Grav is pulling down, but another force, the normal force, pushing this way over here. Okay? So Newton's second law actually would be the weight plus the normal force equals mass times acceleration. Okay? Now the normal force is perpendicular to the surface in the direction of y, so it doesn't have direction in the x component. So if you take the x part, you have wx plus nx equals mass times ax. Okay? Now we just saw that this one is mg sine theta, this one is mg sine theta, but this one doesn't have component in the x direction. If you want, its angle is 90 degrees and cosine of 90 is 0. So we just have this one, and we just conclude this just equals the acceleration, mass times acceleration. So we get an expression for the acceleration of the which is g sine theta. Okay? So the acceleration down a plane, if there is no friction, is simply g sine theta. Alright? Now, let's use the y part of the equation. The y part would be the y of the y plus the y of the normal force equals mass times the y of acceleration. Now the acceleration is parallel to the surface, parallel to the x-axis, you know. The acceleration is this way, it's my x-axis, so it doesn't have component in the y direction, okay? So ay is 0, so this is 0. And wy, you just obtain over here is negative mg cosine of theta, okay? It is negative mg cosine of theta. The direction for the normal force is 90, so if you want, you can say n sine of 90 equals 0, okay? But sine of 90 is 1, so we get n equals mg cosine of theta. So the normal force equals mg cosine of theta, and the acceleration down the plane is g sine theta. Okay? So the acceleration is g sine theta. The acceleration is g sine theta, and the normal force is mg cosine of theta. Okay? So now we're going to assume there is friction. B, assuming there is a coefficient of friction mu. So in this case we have another force, okay, and the force of friction is going to oppose the motion. So the acceleration this way, so we have another force this way now, which is friction. Okay, so in this problem, technically the Newton's second law would be, we've got force of friction, we got normal force, we got the weight equals mass times acceleration. This is our equation now. Okay, now let's look at the force of friction. You see, the force of friction is opposite the acceleration. This is our 0 angle, this is our x-axis. So the direction of friction is 180 degrees. So for friction, we have the following. Friction, well, its magnitude is mu times normal force, okay? And its direction is 180 degrees, okay? So if you look at the x part of the equation, we have fx plus nx plus wx equals max. Okay, so fx would be this mu times the normal force, and then the normal force does not have an x component. Okay, so you get plus 0. Oh, I'm sorry, it's cosine 180 over here. This is friction mu n times cosine of 180 degrees. Okay, that's the angle for friction. Nx does not have any component, plus 0, and wx we just saw over here is this one, mg sine theta plus mg sine theta equals mass, and this ax simply equals the acceleration as we said before. Okay, so this is -1, so we've got minus mu times the normal force plus mg sine theta equals mass times acceleration. Okay, now we have to solve for n using the vertical equation. Okay, so let's go to the vertical equation now. The vertical equation is fy plus ny plus wy equals 0. The acceleration does not have a component in the perpendicular direction. In other words, angle is 0 and sine of 0 is 0. Get this way. So fy, friction does not have component along the y-axis. This is 0. And ny, its angle is 90. So we've got n sine of 90. And wy, we already did it. Ny is over here. Is negative mg cosine of theta. So we've got minus mg cosine of theta equals 0. Okay, this is 1. So we just get the normal force equals mg cosine of theta. Alright, so that's the normal force. Now we can plug this in into this equation over here. And that equation is minus mu n plus mg sine theta, mg sine theta equals mass times acceleration. Okay, so we have minus mu mg cosine of theta plus mg the sine of theta equals ma. Okay, so we can divide by m the whole equation. We get this one over here. So we have the following formula for a equals g the sine of theta minus mu g cosine of theta. Okay, so this will be the expression for the acceleration if there is friction. Okay, when mu equals 0, just recover the acceleration for the case where there is no acceleration. All right. Okay. Next, we're going to look at systems involving two objects. Systems involving more than one, but let's look at two objects. Okay, the general rule is apply Newton's law to each object. Okay, so the general rule is apply Newton's second law to each object. Okay, so let's look at some examples. Suppose, let's say we have two objects. Let's say this is M1, and then attach it to another object M2 by means of a string, and then we have force F pulling this way. Okay, so this is a string, so we have a tension. Over here, the tension is pulling this way, and this object is pulling this way. Okay, so we've got a tension T over here. All right, so we have to apply Newton's second law to each object. We're going to assume no friction, assuming no friction. Okay, so if you assume no friction, this is the only force acting on M1. Okay, so for M1, applying Newton's second law to M1, you get, and both of them are object together, they're moving together, so T equals M1 times A. They both have the same acceleration, right? But if you look at this object, you get two forces. You get this force pulling this way, you get this one pulling to the left. So the force acting on this object is F minus the tension. Okay? So from Newton's second law, you get F minus the tension equals M2A. Okay? So this is an equation for M1, it's an equation for M2. Okay? Our goal is to solve for acceleration, so we can substitute for T by M1A over here. So we've got F minus, for T we put M1A over here, equals M2A. Okay, so we get force equals M1 plus M2A, and then of course we get acceleration equals F over M1 plus M2. Okay, so if you've got two objects, the general rule is apply Newton's second law to each of them, then combine. Okay, another example. Suppose, let's say we have a table over here, and then we have M1 over here. Maybe there is a frictionless pulley over here, and then we have this object over here, M2. Okay. A, we're going to say assuming no friction. A, obtain an expression for acceleration. Let's say obtain an expression for acceleration. Okay. A, assuming no friction. Assuming no friction. Okay, that is between the table and this object where there is no friction. So let's apply Newton's second law to both objects. Let's look at M1 first. The Newton's second law, the only force pulling this object is this tension. Okay, we don't have friction, so that's the only force. And both objects will move the same acceleration, right? So the equation for this one would be T equals M1A. Okay, now let's do the same thing for M2. For M2, look, you got gravity pulling down, that's M2G, and then you got the tension pulling down, pulling up, and the acceleration is downward. So assuming down is positive, the net force is M2G minus the tension. Okay, that equals M2A. So these are our two equations. Okay, and then of course we can substitute M1A over here instead of T. So we have M2G minus M1A equals M2A. Okay, so we get M2G equals M1 plus M2A. Okay, and then we get the expression A equals M2 over M1 plus M2G. Okay, so this would be the expression for the acceleration. B, let's say assuming the coefficient of friction is mu. The coefficient of friction between M1 and the table is mu. Okay, now we have an additional force on M1. You see, we have an additional force F over here. So the equation for this one is going to be tension pulling this way, friction opposing it. That's the net force. So for M1, the equation becomes tension minus friction equals M1A. We're using the same acceleration for both because they're moving together. Okay? Now, what does friction equal to? Friction equals mu times the normal force. Alright? So what do we have over here? We've got normal force pushing up. You got the weight pulling down. Okay? But there is no vertical motion, so these two forces must be balancing each other. Okay? So the normal, in this case, equals the weight, which is m1 times g. Okay? So the equation for m1 would be T minus mu m1g equals m1a. Okay? So this is our equation for m1. Tension minus the force of friction equals m1a. Now if you go to the second one nothing has changed yet. It will be m2g minus t equals m2a. Okay? For m2, we have m2g minus the tension equals m2a. Okay? So we have these two equations. Then put the second equation at the bottom over here. It is T minus mu m1g equals m1a. Okay? Now, if you add these two equations, the t will go away. Okay? Negative t plus t is 0. So just adding, we get the t goes away. We get m2g minus mu m1g equals m1 plus m2a. Okay? So the acceleration is m2g minus mu m1g divided by m1 plus m2. Okay. Another example. Suppose we have a pulley over here. Okay. We've got maybe this is the bigger mass. This is m2. And then we have a smaller mass. Let's say this is m1. And this is m1. Okay. So the question is, obtain an expression for the acceleration. Obtain an expression for the acceleration. All right. So first, this is m2, this is m1. Okay, so we've got tension pulling up over here and tension pulling up over here. The tension in the string is the same all the way, assuming the mass of the string can be neglected. Okay, so let's do m1. M1, what are the forces? You have tension pulling up. You got m1g pulling down. Okay, but this is bigger, it's going down. So we can say m1g minus the tension equals m1a. How about this one? We've got the weight pulling down, okay, but it's going up, smaller. So we'll say t minus m2g equals m2a. Okay, now if you add these two equations, adding, you see negative goes over with t, and we get m1g minus m2g equals m1 plus m2a, and that gives us acceleration equals m1 minus m2g divided by m1 plus m2.